This is joint work with Pavel Kupek, Luciana Xiao, and Sijin Yao, and we have a preprint which is available on my website, which you can see down here on the slide. So my plan for the talk today is to give you a quick motivation for the study of Diophantine geometry, and then introduce some of the recent techniques that have been developed in order to explicitly determine rational points on curves. And then I'll come to this recent result we have, and hopefully, if time permits, I'll say a little bit about the strategy. Okay, so let's get started with the motivation. So my motivation here will come mainly from some classical Greek questions and also the theory of elliptic curves. Okay, so the first question is very old, and it's problem 17 of the 6th book of Diophantus, Arithmetica, and it says the following. It says, find 3 squares which when added give a square, and such that the first one is the square root of the second, and the second is the square root of the third. So this is a little bit contrived, but if you think about it, it asks for rational solutions to the following polynomial equation in x and y. Okay. Another question that I will use for motivation comes from Sayre's uniformity question. So this concerns elliptic curves. And so in fact, whenever you have an elliptic curve defined over Q and you choose a prime L, you can consider the action of the absolute Galois group of Q on the L torsion points of your curve. This gives rise to what is called the residual Galois representation of E at L. Okay, and so it's a homomorphism from the Galois group into GL2 FL, where FL is the field of finite of L elements. And so one may ask, well, for which elliptic curves and which primes is this Galois representation surjective? And so Sayre's question is a uniformity question. So he asks whether you can find a constant n independent of L and the elliptic curve such that for any L greater than n and any non-CM elliptic curve, this Galois representation is surjective. Okay, and so this question here may be rephrased in terms of moduli spaces of elliptic curves, parameterizing some extra structures concerning these Galois representations. Okay, and so this can be transformed into a problem of finding rational points on certain modular curves. Okay, and because these modular curves are algebraic curves over Q, they're actually defined by certain equations, and therefore, again, this is really a question about finding rational solutions to polynomial equations. So what these two questions have in common can be formulated as follows. They can both be restated as asking for solutions to certain Diophantine equations. Okay, and so let me just finish the motivation here by mentioning that, well, the answers to these questions, sometimes partial, are quite recent actually. So for the first one, which dates back to Diophantus, the answer came in the form of Wetherell's thesis in 1997. Okay, so we had to wait a very long time to have some more modern techniques in order to provide an answer to this question, this really simple question. And Sayre's uniformity question was posed around the 60s, 70s, and it's still open today. But some of the most striking recent progress that has been made comes from the work of Balakrishnan, Dogra, Müller, Tuitman, and Vonk from 2019. Okay, so this is just to say that, I mean, the study of Diophantine equations is a very old field, but some of the solutions we're only starting to see them now with the development of more recent techniques. Okay, so I'll come back to the specific solutions to these problems later in the talk. Okay, so a little bit more about Diophantine geometry. So I already mentioned this interplay between Diophantine equations and asking questions about points on curves. Okay, and so here I'll take this point of view of algebraic geometry. And so let CK denote a smooth projective curve of genus G defined over a number field K. Okay, and so what Diophantine geometry means for us here is really the study of the set of rational points on this curve. Okay, and for simplicity here, I mean, we want to study this set, and I'll assume that it's non-empty. Okay, so okay, if one wants to tackle this question, you might want to categorize your curves. Okay, and so one can use this genus to classify curves into different categories. So for genus 0, such a curve will either be a projective line or a conic. Okay, and so as you might expect, as you might expect, this is not a very difficult question, and this was settled by Hilbert and Hurwitz, who established that the set of rational points is infinite in this case. What about genus 1? Well, this is a very particular case. It's the case of elliptic curves. Okay, so not only is this a set, but the rational points are actually endowed with an abelian group structure. And so what Mordell and Weil showed was that this is in fact a finitely generated abelian group, which means that you can write it as a finite torsion part direct sum with some free part. Okay, and so this non-negative integer r is called the rank of the elliptic curve, and this is the key object of study in conjectures such as the Burton-Swenson-Dyack conjecture, for example. And finally, the third category of curves are higher genus curves. So curves whose genus is greater or equal to 2. And so it originated with a conjecture by Mordell, and finally was proved by Faltings in '83. And they showed that in this case, well, the set of rational points is finite. And subsequently, there were more recent proofs, one by Vojta and a very recent one by Lawrence and Venkatesh. So for these higher genus curves, well, it's actually a well-posed question to ask, well, now that we know that this set is finite, how do we explicitly determine it? Given a curve, how can we determine exactly the set of rational points? And so one of the main problems is that all these proofs of Mordell's conjecture are not effective. Okay, so there's no general algorithm that will spit out the set of rational points. So recently, some techniques have been developed to address this question of effective determination of rational points. And so it all starts with the pioneering work of Chabauty from 1941. And so this was actually the first significant progress towards Mordell's conjecture at the time. And so what Chabauty did is he showed that for a high genus curve, the set of rational points is finite if the following assumption is satisfied. So the rank of the Mordell-Weil group of the Jacobian of the curve must be strictly less than the genus. Okay, and this is sometimes called the Chabauty condition. Okay, and so the key point of his method is he considers a prime of good reduction, and he embeds the rational points of the curve into the p-adic points. Okay, and then he embeds the curve into the Jacobian. So these vertical maps here are what's called Abel-Jacobi embeddings. Okay, and then Chabauty considers the p-adic closure of the Mordell-Weil group inside this p-adic Lie group. Okay, and then by studying the intersection of this closure with the p-adic points of the curve, he shows that this is always finite, and therefore the set of rational points is also finite since it's contained in this intersection. Okay. Well, later on in '85, Coleman came along and he made this theorem of Chabauty effective. So he came up with an explicit bound for the number of points on any curve of higher genus satisfying this R less than G condition. So this is the bound that he gets. And here you see the Chabauty condition. He also needs the prime to be greater than 2G. And as I mentioned before, P is good and unramified prime. Okay. And so the main technical innovation here is to consider the log map from this p-adic Lie group and consider the composition with the Abel-Jacobi map. And Coleman reinterprets this map as being a p-adic integral, or now called a Coleman integral. And so by counting the number of zeros of certain p-adic power series, he can bound the size of the group of rational points, the set of rational points. Okay, and let me just mention further that there's been improvements by Stoll and Katzurek-Brown that kind of remove this condition of being a good prime. That's it for the Chabauty-Coleman method. And in the mid-2000s, Min-Young Kim initiated a fascinating program, which is now known as non-abelian Chabauty, or the Chabauty-Kim method. And so his aim is to relax this stringent condition R less than G by considering non-abelian unipotent quotients of the fundamental group of the curve. Okay. And so this is a very vast program, but the first non-abelian instance of it is known as quadratic Chabauty. Okay. The first instance is quadratic Chabauty, and this method was recently made effective over Q by Balakrishnan and collaborators of hers. Okay? And so it kind of improves this Chabauty condition to R less than G plus rho minus 1, where rho is the rank of the Néron-Severi group of the Jacobian of the curve. Okay? So imagine if rho is 2, then you can actually treat curves for which R equals G. Okay, so this is exactly, it just goes beyond the scope of this Chabauty-Coleman method that I told you before. Okay, even more recently, there's been the new development. So the geometric quadratic Chabauty method was initiated by Edixhoven and Lido in 2019. And this is a new effective approach to Kim's quadratic Chabauty method over Q. Okay, so this is, it avoids this language, Kim's language of non-abelian p-adic Hodge theory, and replaces it with more down-to-earth language of line bundles on curves and on Jacobians. Okay, so this is a more geometric method, hence the name. Okay, so now that we've seen, these are kind of the state of the art of the effective methods that exist today. And so let me go back to the motivation from the beginning, okay, and tell you what the answers are. So for this problem of Diophantus, as I told you, the answer came in the form of Wetherell's thesis from '97. And so it turns out that the only positive rational solution to this polynomial equation is the one given by Diophantus himself, which is x equals 1/2, y equals 9/16. Okay, and so how does Wetherell prove this? Well, with techniques that were definitely not available to Diophantus at the time, he uses Chabauty-Coleman on the following hyperelliptic curve, whose affine model is described by this equation here, and it has the feature that R equals G equals 2. Okay, so if you remember this Chabauty condition, well, this hyperelliptic curve does not fall within that scope. Okay, so actually Wetherell, he further develops the method and uses what is called Chabauty-Coleman bicovering of the curve. Okay, but maybe more appropriately, very recently, Francesca Bianchi has obtained the same result using this new quadratic Chabauty method of Balakrishnan. Okay. Okay, so that's it for Diophantus' problem. What about Sayre's uniformity question? So the common belief is that for any prime L greater than 37 and any non-CM elliptic curve, the residual Galois representation is surjective. Okay. So how do you tackle such a question? Well, if the Galois representation is not surjective, then it must land, the image must land in some maximal subgroup of GL2FL. And these can be categorized as being exceptional groups, Borel subgroups, split Cartan, or non-split Cartan. Okay. So the first results came from Sayre, Mazur, and Bilou-Parent-Rebolledo. Okay. So Sayre took care of the exceptional case, Mazur took care of these Borel subgroups, and Bilou-Parent-Rebolledo worked on the split Cartan case. So they were able to settle all cases for any prime except the prime 13. And so very recently, in a striking new result, Balakrishnan, Dogra, Müller, Tuitman, and Vonk, in their Annals paper from 2019, they dealt with this so-called cursed curve, which is the split Cartan modular curve of level 13. And so they proved that the only rational points are either CM points or cusps. And so this ends, together with the work of Bilou-Parent-Rebolledo, this ends the classification of split Cartan elliptic curves. And let me just say that the method they use is, of course, this new recent method of quadratic Chabauty for this curve. And it has R equals G equals 3. So the previous Chabauty-Coleman method could not be used. And there was no available tricks with coverings like Wetherell did. So this was really a case that no one knew how to do. Let me just finish by mentioning that the non-split case is still wide open. And in fact, by some sort of coincidence, at level 13, the split Cartan modular curve is actually isomorphic over Q to the non-split Cartan curve. So this result, this recent result, also provides the first case, the first advance in the direction of non-split Cartan. Okay, so having seen this, well, one may ask the natural question of what about generalizations of these explicit methods to number fields? Okay, so let me go back to the setting of a number field K of degree D. And so here I'll call R1 and R2 respectively the number of real embeddings and the number of pair of complex embeddings of the number field. Okay. So it all starts with the work of Samir Siksak from 2013, where he does effective Chabauty-Coleman over number fields. Okay, and so this Chabauty condition from before, which read R less than G, now in this setup becomes R less or equal to D times G minus 1, where D is the degree of the number field. Then the work of Balakrishnan, Besser, Bianchi, and Müller did the same work, extended the effective quadratic Chabauty method to number fields, using similar techniques at Siksak, meaning Veil restrictions of Jacobians. And what they obtain is this Chabauty bound here, Chabauty condition. There's also work of Netan Dogra, more on the theoretical side of Kim's quadratic Chabauty method, where he bumps it up to this Chabauty condition. And finally, there's my joint work with Kupek, Xiao, and Yao, where we generalize this geometric quadratic Chabauty method of Edixhoven and Lido to the setting of arbitrary number fields. And so you'll notice that we recover the exact same Chabauty condition as the one for quadratic Chabauty over number fields. So let me give you just a rough idea of what our theorem looks like. So suppose you have this condition, okay? And suppose you're working with a curve, smooth projective curve defined over the number field of genus G, greater or equal to 2. Let delta be R1 plus R2 minus 1. And consider this ZP algebra, which is the p-adic completion of the polynomial ring with ZP coefficients. Okay, so these are formal power series which have certain convergence conditions on them. Then we construct an ideal I of A with the following property. So if the reduction of the quotient of A by I, modulo P, is a finite dimensional FP vector space, then we're able to say that the size of the set of rational points of the curve we started with is bounded by this dimension. Okay. So let me just mention here that this statement is greatly simplified for the sake of exposition here. We really work residue disk by residue disk. Okay, so there's a lot of technicalities coming into this type of result. And also let me mention that we do not use Veil restriction of the Jacobian or on the object to descend the problem to work over Q. We actually deal directly with geometry over K, and more specifically, we actually have to spread out to work over OK, the ring of integers of K. So I see I have 1 more minute left. So let me maybe just very briefly outline a very simplified strategy. So the basic idea of Edixhoven-Lido, whose method we generalize, is to replace the Jacobian in Chabauty's original method by something bigger. And what is that? It's a certain GM to the rho minus 1 torsor over the Jacobian. Okay, and so it arises as a certain pullback of the Poincaré torsor over the Jacobian times the dual Jacobian. And by construction, it comes equipped with a certain lift of the Abel-Jacobi map. So we can consider a Chabauty-like diagram, if you remember the one from the Chabauty-Coleman method, where these vertical maps are the lifts of the Abel-Jacobi maps. And once again, we embed our rational points into the p-adic points and consider the p-adic closure now of the rational points of this torsor. And the aim is now to bound and compute this intersection. Okay, thank you very much for your attention.
Thank you.